And we will start from current slide. And I may even turn on the projector for you. The only announcements, you know, the math team meets every Monday, 3 o'clock, and every Friday, noon, over on the Birmingham West campus. That's at the C building, which is the science building, C100, with Ms. Rossi, the coach. And tutoring, if you need it, they've got it down the hall here at Student Support Services and also down in the Space Center. But even more so, I think you should be tutors if for any of the classes you've had below this. Oh, you know, this really irritates me. How they make me plug in the projector that won't just come on its own. It seems like they could fix technology so I don't have to do this. Okay. All right. Let's see if I can get this to set up now without breaking something. All right. Yuck. I'm about to break something. Pulling it off the desk. Okay. Is it power? Yeah. All right, good deal. Now, we're in Chapter 3, Applications Differentiation, Section 3.6, Summary of Curve Sketching. We're at example 3, which is the top of page 212. Any questions on anything we've done up till now? Okay. The last thing we did was the follow-up with slant asymptotes, and I have a feeling if they, they don't show that for example 3. They don't have example 3 on here. Let's see if I can find, like they don't have anything past example 1. So we'll use that slide to write example 3 on. Sketching the graph of a radical function. Okay, we haven't done any radical functions lately, so let's get this one. Well, my pen is not working yet. Now it's working too well. Okay, let's get this done like this. Okay. Example 3, top of page 212. Analyze and sketch the graph of this function. F of x is equal to x over the square root of x squared plus 2. Okay. Now, a lot of what we said with rational functions, when you had a polynomial over a polynomial, some of that same sort of stuff you have to pay attention to now. For instance, okay, what can you think of something we have to watch for? Zero in a denominator, okay? And for you to have a 0 in the denominator, that would mean that the square root of this thing had to be 0. Well, the only way a square root can be 0 is the thing inside the radicand is 0. Can x squared plus 2 ever be 0? No, it can't. So we have no vertical asymptotes in this problem. The denominator is never equal to 0. Okay? There's something else that we worry about. Okay, give me some other things we concern ourselves with rational equations that we could still use here. We've already eliminated the possibility of a vertical asymptote. What else might we concern ourselves with? Okay, now that one's sort of interesting. I was wondering if someone was going to think of it. I'm going to make a guess here, and I'm going to tell you why, okay? Usually what we do for rational expressions is do the ratio of the leading terms. Okay, this is a radical down here, so it really doesn't have a leading term, but you can kind of treat that as if it was the square root of x squared, which would be in square root of x squared, x, and x over x would seem to be 1. So I'm going to write it like this, okay? Vertical asymptote, none. Horizontal asymptote, y equal 1 with a question mark. I don't know for certain if that's going to be the case, but we're going to investigate to see if it is, okay? Those are two things we look for with rational functions. What's another we did? Throwing Elijah the ball, and Terrell jumps up in. Say again? Intercepts it. Ah, okay. Nick would be proud of it. Okay, now, how about our intercepts? How do we go about finding those? What two types of intercepts could we have? X and Y intercepts. Which you want to go for first? X. What's true about an X intercept? Where? Y equals 0. And what's your Y in this problem? F of X is Y. Okay? And how in the world could this be 0? If and only if your numerator was 0. So X equals 0 is going to be an x-intercept. And what is the y value when x is equal to 0? Zero. So guess what? That's not just an x-intercept. That's a y-intercept as well. Both of your intercepts are 0, 0. Okay. All that we got from the same rationale and the same strain of thought that we did when we were doing rational functions. Okay? Now, there's something else to take in mind here. Before, we were concerned only when denominators were 0. We've already dealt with that. Okay? But here, as soon as you see a radical, no matter where it is, numerator, denominator, or wherever, what have you got to concern yourself with? What about the radical?
Rewrite it.
Okay. You could do that just for aesthetics, but I mean for the inherent problems that come with radicals. What does the radicand have to be? Especially if this is a square root or a fourth root.
Oh, it has to be positive.
Ah, very good. And how do we express that mathematically? What's inside there, which is x squared plus 2 has to be
positive.
Yeah, but how do we express it mathematically? Symbolic.
Greater than 0.
Greater than or equal to 0. It could be 0, okay? We've already said it couldn't be 0, so greater than 0. Well, guess what? That radicand is always greater than 0. For all real numbers x, positive, negative, any real number x, square it and you get a positive number. Except 0, and that would be 0. Add 2 to it, and you've got a more positive number. So yeah, no problem there. So we don't have anything to worry about there. Limitations on the domain. So now I guess we're ready to, so your suggestion of rewriting it. Why do we do that?
It makes it easier to look at.
Okay.
Put the fraction out there instead of having to remember that's 1 over 2.
Okay, so how would you rewrite it?
X squared plus 2.
Okay.
1
To the what?
to the 1.
Okay. Where are you writing it?
Out there.
Huh?
Where you are.
Okay. Numerator or denominator?
On the bottom.
Okay. Oh, you're writing it on the bottom. So yeah, that would be x over to the 1/2. Right. Okay. I'll agree with that. Okay. But I really don't like that a lot more than the radical. It's a little bit better. I actually like that as x times x squared plus 2 to the, if you bring it upstairs, negative 1/2. Now, that's just my preference. I don't mean to drive you away from the quotient rule if you like the quotient rule. I just tend to like the product rule a little bit better. To me, it's easier to deal with. Okay? But if you like quotient rule, this form is perfectly good. Okay? So it just depends on which one you want to go with. Once you got it, what are you going to do with it? Clark likes it just because it looks better. He's all about looks, you know. Is there any other practical reason to have done that? Emphasis on practical, okay, besides aesthetics. Ah, very good. So let's take a derivative. F prime of x is equal to, and whichever way you want to do it, it's written both ways. You can either do quotient rule or product rule, whichever you prefer. Which one do you want? Say again?
It would be 1 times
Okay, if you're doing product rule, it'd be 1 times x squared
plus 2 to the negative 1/2.
2, okay, yes, okay, to the negative 1/2. I'm sorry?
Would it be plus? Then it would be plus, and then take the derivative of.
Okay, so you want me to write a plus? Okay, plus x times
2x.
2x, okay, that's fine, times
Say 1/2.
okay, which way are you going with this?
1/2 x.
I think it's going to have to be a negative 1/2,
Oh, yeah.
won't it? Okay, negative 1/2 times what? X squared plus 2 to the
negative 1.5.
yeah, 1.5 would do, or 3/2, either one, okay? I think, therefore I am, that you've gotten it done, okay? Now let's clean it up just a little bit. This would just be, you don't have to write it on the 1, so let's just write it as x squared plus 2 to the negative 1/2. Now let's see what we got. We got a plus, a minus, and a plus, so let's do a minus. We got a 2 and a 1/2. That can multiply away to be 1. That leaves us an x squared in the numerator and an x squared plus 2 to the negative 3/2 as your denominator. But we still have it in the numerator. Okay? I think we've simplified it as far as we can. So let's go back and write it. I think I still like fractional exponents, but let's put them back in the denominator again. This will be 1 over an x squared plus 2 to the 1/2 power. And this will be a minus x squared over x squared plus 2 to the 3/2 power. Okay? Now, if you want to get that in as a single fraction, what would you have to do?
Common denominator.
And which would be?
X squared plus 2 to the negative 3/2.
Okay. So over here, you're going to have to multiply to get that as your common denominator. You're multiplying by x squared plus 2, right? So that'll make that to the 3/2 power, but up here, you'll need an x squared plus 2, right? All right, and when you do that, and you have the same denominator, you could put that all over x squared plus 2 to the 3/2 power, and then you have a x squared plus 2 minus x squared, which is, I'll write it out, x squared plus 2 minus x squared. That leaves you only a 2. Okay? Now, what do you do with those first derivatives? You found it, sure, but why are you interested in it? Yeah, you will, and ultimately do that. But while we're here, let's go and take second derivative. So let's go back and rewrite this, maybe in a little bit easier form to take a second derivative. What would that be? 2 times x squared plus 2 to the minus 3/2, right? That's your f prime. And what's your f double prime? I'm going to write it over here. F double prime of x would then be, okay, take your time. Pay me by the hour, not by the day. No, I'm just kidding. Okay. What would be next? That's your first derivative. In simplest form to differentiate. Kind of like this form for playing with, that one for differentiation purposes. What would be your second derivative? Simple power rule, isn't it? How do you do the derivative of power? Exponent times the coefficient, right? Which would be what? Exponent times coefficient. -3. Don't forget mine. Okay. So that would be a -3 times, that's the first step, the easy step. What's next? Second? Okay, x squared plus 2. So what's in that parentheses to the what power? I see Miles moving, but I can't hear anything.
No, I was just saying I left my calculator.
Oh, you don't need a calculator.
-5/.
-5/2. It drops it by 1. But then you got one more little step, which is? Yes, which is? 2x, okay, times 2x. All right, so writing that a little more reasonably, we would have -3 times 2 would be a -6x in the numerator over x squared plus 2 to the 5/2 in the denominator. Agreed? Okay, now let's go back to this first derivative. Why were we taking the first derivative in the first place?
Find our critical numbers.
To find the critical numbers or critical points, exactly. And how do we find those? What do they have to do with first derivatives? It's where the first derivatives are either equal to 0 or do not exist. Exactly. Now, is that first derivative, I like this form better, ever equal to 0? For that to be 0, the numerator would have to be 0. Is 2 ever equal to 0? No. Okay? So there are no places for the first derivative to equal to 0. Is there any place where the first derivative is undefined? Okay, now what would make that undefined? In the denominator, right? And is that ever 0? No. Okay? Is it ever the part in here negative? No. So there are no places. You have no critical points, which means no relative maxima or minimum. Okay? Now, what else can we worry with? Clark had me go and take a second derivative, so I did. What will the second derivative tell you?
Tell us our curvature, or whether it's
Yes,
increasing or
okay. It tells you things about the curvature, okay? And what does this tell you? What's the points we're interested in there that deal with curvature? Not critical points, but points of
positive or negative?
inflection, points of inflection. And where will they occur? Yeah, if the second derivative is either equal to 0 or undefined. Is that second derivative ever equal to 0?
Yeah.
Where?
And x equals
When x equals 0, exactly. When that numerator is 0, the second derivative is 0. Only time that's going to happen when x equals 0. And that doesn't mess up anything down here, but there's no places where that's undefined, so we only have one potential point of inflection. Okay? And that would be at x equals 0. Okay. What were we supposed to do with this in the first place? Example 3, analyze, and we just sort of analyzed it to death. No, we didn't to death. And sketch the graph of f of x. Now, I did something, sort of ignored something I shouldn't have. Back when we were doing the y-intercept, the horizontal asymptotes, I said you can look at the ratio of these, right? And we said y equal 1 might be 1. What I didn't think about was you could put a minus 1 in here, and a minus 1 in here, but minus 1 squared would be 1, and square root of 1 would be 1. So minus 1 over positive 1 would also be a negative 1, plus or minus 1, are our potential y-intercepts. Horizontal asymptotes, y equal minus 1. Now, I had the question mark by it that we were going to see, and indeed, when I glanced at the graph, I thought, oops, I forgot to mention that one. There, sure enough, we have our x and y-intercept. We have the point of inflection at the x and y-intercept where x equals 0, and that's going to be at the point 0, 0. So everything is going to hinge on that. So we're going to need some test points, one to the left of 0 and one to the right of 0. Now, I don't have room to graph, but I'm afraid if I erase anything, it's going to be something I might need. Is this going to be all right with y'all? It's going to be ugly. Pick me another color. Blue, light or dark?
Carolina.
Huh?
Carolina blue.
Carolina blue, okay. Okay, Carolina blue. I got it, didn't I? I have a little bit of tar right there. I was born in North Carolina, so it was required for me to know what Carolina blue was, even though my dad went to NC State. My uncle went to NC State, okay. Nephew went to Wake Forest, yeah, never mind. Okay, but I still know what Carolina blue is, sort of. That's not quite light enough, but it's close. Okay, we have 0, 0 as our point of inflection, and we have, let's just put this as our y equal 1, and that's going to be our horizontal asymptote, we think, and we'll do a y equal minus 1 down here, and that will be our second horizontal asymptote. No vertical asymptotes, only one intercept, 0, 0, x and y intercept, and the one point of inflection, no extrema. So we need a test point. You want one to the right, one to the left of 0. What would you like to choose for your test point? Okay, why such big numbers? About -1 and +1. Aren't they going to be a little easier? Maybe not, but let's see, okay? When we plug a -1 into f of x here, what do we get? F of -1. I'll write it over here where I've got room. Numerator will be -1, right? F of -1 is x, which will be -1 over the square root of, what's -1 squared? 1 plus 2 is 3, square root of 3. If someone's got a calculator, at least give me a value for -1 over root 3. I know it's going to be negative. Fairly small number, less than 1. Oh, what, 0.3? That sounds reasonable. I would have thought. You sure it is the square root of 3? Okay. Ah, that sounds better. -0.5?
Yes.
Okay, so it's going to be somewhere down here. Okay? Let's do the same for f of +1. And I think that's going to be the same deal, isn't it? 1 over root 3, which is about 0.57, you said, something like that? Okay, somewhere about in there. And it's going from there to, let's see, I don't think I got that right. I think my curvature goes up like this and then like that. Okay. And how I have to tell, and it is important, okay? Let's look at first derivatives, and I think a first derivative will tell us a little something. Here's our expression for first derivative, 2 over something that's always positive, right? That's always positive, so the first derivative is always positive. Well, however you draw that, it's going to be positive. So let's look at second derivative. If x is negative here, your second derivative is positive, meaning concave up. So therefore, the second curve I drew, I had to have it concave up. And when the x is positive, then the second derivative is always negative. So I have it concave down. So you do have a point of inflection here, going from negative, positive to negative, and passes to 0 right in there. Okay? So that's how it looks. I'll just bang my knee. Okay. Let me see if I can clean this up just a little bit. Not that line, but that one. Concave up to the left, concave down to the right. If you take a look at the book, their picture doesn't look quite as good as mine, but, you know, it's somewhat close. Okay. All right. See, I knew I'd need my first derivative and second derivative and function, so rather than rewriting them all, we've got that. And see, what I don't understand in their table is in their f of x's, for negative infinity to less than 0, less than 0, negative infinity less than x less than 0, why don't they have f of x is always negative there? Because it is, okay? Okay? And it's 0, x equals 0, and it's always positive from 0 less than x less than positive infinity. Why didn't they put their signs in there? First, they may not think you care what the signs are, but I think you do. First derivative is positive everywhere, and sure enough, it's sloping upward everywhere, including the point of inflection. And then the second derivative is positive on the negative side, negative on the positive side of 0, so, and 0 at 0. So we've got the point of inflection. Okay, that's about it, right? Now, not all radical expressions, equations will do that. This came out special, mostly because the denominator is where the radical lives. On this side, the radical is neither 0, which would have given us a vertical asymptote, nor was it ever negative, which would have given us a break in the, continuity, you might say. All right, can we move on to example 4? Anyone need this up a little bit longer? You got it? Everybody? Okay. So example 4, which they don't have. Oh yeah, you got to go, don't you? Okay. Sketching the graph of another radical function. Okay. Analyze and sketch the graph of this one. F of x is equal to 2 times x to the 5/3. Hate to be leaving one like this, don't you? Okay. Minus 5x to the 4/3. Okay. Now, one like this is going to be a whole lot harder to try to do, because this doesn't even look anything like your rational function. I mean, there's no anything in the denominator. Everything here is in numerators. So we don't go through asymptotes and that kind of things. We just light out and start doing stuff. So what would you suggest we do first? Well, I guess we could do, just looking at this. What's that? Yeah, that's exactly what we're going to use when we start differentiating, is the power rule. You're absolutely right. But while we had it in functional form, what we might do is look at our zeros. We don't have any asymptotes here, but we can deal with zeros. What's true about a zero? What types of intercepts do we have? Well, we usually call them x's and y's. The asymptotes we call vertical and horizontal. And what's going to be true about an x-intercept? What's equal to 0? No, x equals 0, you have your y-intercept. Now think about this. Okay, x equals 0, you're neither right nor left, so you're somewhere on the y-axis. So x equals 0, it's a y-intercept. And therefore, where? Flip that around. Where y is equal to 0 is it? X-axis. So that's going to be your x-intercept. So which one you want to do first? Second? X-intercept. So where y is equal to 0. So this is going to take a little bit of head scratching here. What we have is y, that's your f of x, is equal to, I don't know if this is going to be helpful or not, 2, I'm going to write it as a radical. I probably will regret it, but I will. 2 times the cube root of x to the 5th minus 5 times the cube root of x to the 4th. Okay? Now, where y is equal to 0, you want to do x-intercept first, right? Where y is equal to 0, then set that equal to 0. Now that says that 2 times the cube root of x fifth is equal to 5 times the cube root of x fourth. Okay? Now, what I would be tempted to do in a problem like that is cube both sides. Okay? To get rid of the roots. Okay? So this will be 2 cubed is 8 x to the fifth, right? Because when you cube a cube root, you just get what's under there, right? Is equal to, and when you cube a 5, you get 125. Excellent. I can't write it, but I can say it. Okay, 125. Let me see if I can clean that up just a little bit. Okay, 125 x to the fourth. Okay? Now I think I'm going to go back and take them to the same side again. 8x to the fifth minus 125 x to the fourth equals 0. Okay? Where do we go from there? Factor! Excellent. What would you factor? Oh, come on. What's your greatest common factor? X to the fourth times 8 x minus 125. Now, if you were looking to see if there are any common factors between 8 and 125, they're not. Remember, how do we get the 8? We raise 2 to the third power. 2 times 2 times 2. How do we get 125? 5 times 5 times 5. No common factors at all there at all. 2s and 5s, nothing in common. What's that? Right, exactly. Okay. That's equal to 0. What does this give you? X equal, got two products equal to 0. You factored. You had something equals 0. What you do with it now? You have a product of two entities here equals 0. What does that tell you? Either this was equal to 0 or that was equal to 0, right? So this will, first, to be more thorough about it, x to the fourth equals 0, or 8x minus 125 is equal to 0. So x to the fourth equals 0. What's the possible values of x to make that 0? X equals 0. That's it. X equals 0. However, that has a multiplicity of 4. Right? What does that tell us? That tells us a diamond is here. Okay? That's what it tells us. Okay? Okay. We're doing example 4 on the bottom of page 212, chapter 3, application differentiation, 3.6, summary of curve sketching. What does that tell you? Multiplicity of 4? It's an x-intercept, right? X-intercept, where y was equal to 0. So that x equals 0, wherever it's coming from. I don't know where it's coming from, but it's either coming down to x equals 0, then it's going to linger a while and then go back up, because it's an even multiplicity. If it's odd, it's going to cross, even kisses and goes back in the same direction. Could be from down here like that, but it doesn't cross. It only kisses. Okay? How about the other one? What does that tell you? Add 125 to both sides. And that gives you 8x equal 125. And then you divide by size by 8. That gives you x approximately equal to, that would be 1 with 4 left over. That would be 5 with 5 left over. 8 will go into 56 times 625, I think it is. Check that out and see. Punch it into your old calculator and see if you get that. What's that? That's it. Good deal. Okay? I've got to watch myself. I just about pulled my computer onto the floor again. All right. So there is your other x-intercept. X equals 0, multiplicity of 4. X equals 15.625. Or you could say 15 and 5/8. Okay. So we got our x-intercepts. Anyone want to make a guess on the y-intercept? How do you get it? You know, not yet. You could, but y-intercept is going to be where? If the x-intercept is where y is equal to 0, then y-intercept is where x equals 0. How many of those can you normally have? If it's a function, one and only one, because the y-axis is the vertical line. How many times can a function cross any vertical line? Once and only once. Or it may not cross at all, but it can't cross more than once. So we usually don't. So we'll say x equals 0. When x equals 0, what does this give us? 0 minus 0 is, so our x and your first y-intercept is at 0.00. X equals 0, y equals 0. Okay? So there's your y-intercept. So x-intercept, you have 0, 0, and 15.625, 0. Okay? Y-intercept is the same as this one. Is also 0, 0. Okay, we got that done. Now, I heard you chomping at the bit, and since I wrote those up here, I'm going to erase all this other stuff. Is that okay? Y'all all right with it? Okay. So let's erase this. Okay, we got that. Now, what do you want to do next, you said? Take a derivative. Good answer in our Cal 1 class, okay? And what would that be? A little louder? 5/3, yeah. The second one's 4/3. It's what? And what would that give you? Say again? I can't hear. 10 over 3. 10/3 times x to the... Say again? Really? You're reducing it by 1? 4. Okay, yeah. Okay, but the 5/3 would be, reduce that by 3/3 and you get 2/3. Did I hear 2/3? I was hearing 1/3. Okay, yeah, 2/3 is right. Okay, good. Okay, minus 20/3 times x to the, second? Help me. 1/3. Okay. Now, why do we want to get a first derivative anyway? What does that help us with? What does that tell us? Say again? Test point, critical points. Okay, let's call them critical points. Test points will be later. Okay, critical points. Where will you have your critical points? where the first derivative is equals 0 or not defined. Okay. Now, are there any places where that's not defined? No, you can plug in any value when you're taking a cube root, which is something through the 1/3 power, you can put any value in there. Nowhere that's not defined. If that was 2 in the denominator of the exponent, yeah, you couldn't have any negatives in there. But with 3s and 5s and 7s, you can have any value you want to in there. So there's no places where it's not defined, so we're only interested where it's equal to 0. So let's go back and do that again and set this equals 0. Okay? So let's write what our equation is then. 10/3, and I'll rewrite this as the cube root of x squared minus 20/3 times the cube root of x, right? Equals 0. Now, what would you suggest we do next? Say again? Both are cube roots. One's an x squared, the other's an x. Okay, except we only really have one side. Zero's on the other. Let's move this to the other side. 10/3 times the cube root of x squared is equal to 20/3 times the cube root of x. Okay. Now, actually, before I cube both sides, anyone else want to suggest something we could do? What's messy about that? Factors? Is that what you said? Or fractions?
I say fractions.
Fractions, yes, exactly. So how can we clean up those fractions a little bit? This is an equation now, okay? So we can use all the rules for equations if we want to. What would we do? Anyone in favor of multiplying both sides by 3? Oh yeah! That'll make it look a lot nicer, won't it? In fact, I'll do it right now. Done. Even with sound effects. Notice that? Okay? Now, what else can we do? Now that we've done that. We have 10 times the cube root of x squared is equal to 20 times the cube root of x. What's sort of messy about that? I know the cube roots can't do anything with that. But
Did you divide 10 both sides?
yes, divide 10 both sides by 10. So this one, you do that same sound effect, okay? And loses 0, okay? Now let's go back to on the same side and see what we, no. Now we cube both sides. And what does this give us? X squared, no. Right? Okay. Is equal to, say again? No, that's a 2. 2 cubed is 8x. Right? Okay. Now let's get them back on one side. Just sort of moving them around. X squared minus 8x is equal to 0. And now what can we do? What'd you say? I can't hear you, a little louder.
I was saying the differences of squares, but no, that's not very.
Say again?
The differences of squares.
8 and x, neither one are perfect squares. Simpler than that. Factor! What would you factor? X, and that leaves you x minus 8. And what would that tell you? Yeah, either set it equal to 0, and that would be either x equals 0, multiplicity of 1, and x equal 8, multiplicity of 1. Oh, but we're not worried about that on the first derivative. So this gives us what? What does setting a first derivative equal to 0 give us? It's critical you know that. Critical values. All right, very good. Okay, pick right up on it. Okay, your critical values are critical points. Exactly. Okay, x equals 0 and x equals 8. Now we already know x equals 0 is going to be our x and y intercept. Now there are sorts of indications. It could be an extrema or not. Remember, some critical values are not. But we already knew this too, didn't we? Because, remember, I already erased it, but I said that had a multiplicity of 4, meaning it is either coming down and going back up, or going up and coming back down at x equals 0. Guess what? It can't be neither. That's going to be either a max or a min, because it's reversed, not crossing there. So we do know we have a critical value at x equals 0, and at x equals 8, we'll have to see what happens there. We know the first derivative is 0 there. Okay. All right. So we have two potential critical values. Anything else you want to do? To first derivatives. Second derivative, why not? Good idea. Okay, let's take the second derivative. F double prime of x, and what's that equal to? Using these, okay? Kind of messy fast, but what does it? Is that a little louder? Did I hear 29ths? No. What did I hear? Okay, yeah, that's what 2/3 times 10/3 is 29ths x to the second. Negative 1/3. Right, negative 1/3 minus 29ths x to the negative 2/3. You're subtracting 3/3 from 1/3, right? That gives you negative 2/3. Okay. Same coefficients here. That looks interesting. Now, yes, we set it to 0 or where it's not defined. Okay? And let's first set it equal to 0. So that'll be 29ths x to... Can I go on and write that? Because I don't know if it's easy to work with, but it just feels like it might be. 29ths times the cube root of x, cube root of x, minus 20/9 times the cube root of x squared, right? Let's set that equal to 0. All right. So we're first going to say where this is equal to 0. Boy. The 29ths can be factored out, just done away with. And what we have then is 1 over the cube root of x minus 1 over the cube root of x squared is equal to 0. Now, since that's a difference, we need same denominators, so we have to multiply this by the cube root of x again, but we'd have to multiply the numerator by the cube root of x, right? Now this will be the cube root of x squared. Okay, so that's our denominator. So what we have here is the cube root of x minus 1 over the cube root of x squared. Okay, have that equals 0. Now, when's that going to be true? When will that be true? You see what I did? Or was it too much to sleight of hand? This is only going to be true where the numerator is equal to 0, right? It's the only time you have a fraction form equals 0 if the numerator is 0, right? So that, in other words, the cube root of x has to equal 1. When is the cube root of x equal 1? What value of x? No, this is second derivative equals 0. First derivative equals 0, these are critical values. Okay? Second derivative equals 0 will be potential points of, say again? Inflection. Inflection, right, okay. It may be affliction too. No, okay. Okay. So, but when is the cube root of x equal 1? What value for x? 1. Yeah. So that is our one potential point of inflection. X equal 1. Okay? That's where your second derivative is equal to 0. Your other place would be where your second derivative is not defined. And when is that second derivative not defined? Especially if you look at it in this form. Not equal to 0. What would make that not defined? In your denominator. And when is either the cube root of x or the cube root of x squared equal to 0? When x is equal to 0. Yeah, for sure. So there's another possibility where x is equal to 0. This one is where your second derivative is 0, and where your second derivative is undefined is where x equals 0. So we have two potential points of inflection, two potential critical values, okay, which could be or not. Oh, that's interesting. We have a point of inflection and a critical value at the same thing. Ha! That means the first and second derivatives are, no, the first derivative is equal to 0 there, the second derivative is not defined there. This could be interesting, okay? Now, what? Let's do critical, what do they call it in this book? Critical values or critical points? Critical values, don't they call it? Two intercepts, we got that. Two critical numbers. Okay, two critical numbers. X equal 0 and x equal 8. Okay? Now we already know what the y value is when x equals 0. That's 0. We haven't figured out what it is for x. And we have two potential points of inflection. Okay? And that would be x equals 0 and x equal 1. Okay? So, let me erase the rest of this. Sorry about this. All right, to erase. Oh, I really don't want to, do I? I think I want to erase this part. I want to leave those first derivatives in place. Okay. And I want to leave the second derivatives in place. If I can get these things to erase. Okay. I don't know if I'm going to need them, but just in case I do, especially since I wrote them all at the top, lucked out and did that. This is f prime of x equals that. And we'll take off the equal to 0 because we've already dealt with that. And we'll, okay, I think we're okay now. All right, are we ready to roll? I'm not sure we are, but let's try it. Okay. We know that 0, 0 is an x-intercept. You know what? I'm going to change something before I get any further. Okay? I hope I won't regret this. I'm going to put my y-axis over there because it looks like to me all the x's of interest are to the right. Okay? So 0, 0. Let's call this 20 out there. Let's call this 10 here. Call that 5 and 15 there. And we call that 2 and 3 and 1 and 4. 7 and 8 and 6 and 9. 12 and 13. 11. And, ooh, I messed that up, didn't I? Now I've gotten lost. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13. Yeah. Okay. Something like that. Okay. So we're interested in the point 0, 0. Got that one. And then the other one is 15 and 3/8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 5/8 will be somewhere right about there. So those are our two x-intercepts, our one and only y-intercept. We have a critical number x equals 0 and another one at x equals 8. 1, 2, 3, 4, 5, 6, 7, 8. I'm just going to put this as a critical number. And point of inflection, and this is a critical number. Point of inflection, this is also POI, and x equal 1. Woo, goodness gracious, that's a POI. I guess we determined it. That's a POI. Okay, get out of there. All right. So let's pick a point, just one point to the left of our critical point. Point of inflection, let's do a -1. Let's do a f of -1. That would be 2 times the cube root of -1 raised to the 5th power minus 5 times the cube root of -1 raised to the 4th power. Okay? Now what's -1 raised to the third, take the cube root of -1. -1. Cube, you raise it to the 5th power. -1. Multiply by 2, -2, right? Okay? Over there, when you do the cube root of -1, you get I did put my cube there. Cube root of -1 is going to be -1. To the 4th power is -1 to the 4th power is +1 times -5 is -5. So -2 minus 5 is -7. 1, 2, 3, 4, 5, 6, 7. Okay, so we're down here at -1. We're up there at 0. Now, from what we knew before, this was a x-intercept, but it's an x-intercept to the multiplicity of 4. So that means it comes up to that, but comes back down. So if I'm remembering right, am I on the right problem, or was that the last part? No, that was this one. Okay. I believe I'm right. Okay. I believe it comes up and hangs around there and comes back down, and then has a point of inflection here. So it does something like that. Okay. Let's get the value at x equal 1. So what is f of 1? 1's a real easy thing to plug in. 2 minus 5 is -3, right? Just your coefficients. There's a minus, what was that, -8 down there? I can't remember. It's been so long. But yeah, no, -7. 6, 5, 4, 3. Okay, so here we have a -1. At 1 we have a -1. That's your point of inflection. I'm pretty sure you're hanging around 0 for a while here. Then you go down, concave down here, concave up here. Okay, we'll see if that works. Let's do our other critical point here. This was -3. Let's do f of 8. Okay, that would be 2 times the cube root of 8 to the 5th power minus 5 times the cube root of 8 to the 4th power. What's the cube root of 8? Oh, come on, people. Cube root of 8? Say again? I can't hear. No, cube root of 8. Just the cube root of 8. What? 2. Of course it is. 2 cubed is 8, right? So that's 2 to the 5th power is 32, right? 32 times 2 is 64. Okay, remember that, 64. Cube root of 8 is 2 to the 4th power. 16. 5 times 16 is 80. So what did I say, remember this was? 64 minus 80 is minus 16. Is that right? -16. Yeah! Okay, we're somewhere way down off scale here. Let's just imagine it's down here. Somewhere down there. Okay? So here what we've done is we're coming up from here. I'm guessing it's concave down there, concave down here, and then must have a concave up here, a 0, ooh, get out of there, okay, a 0 there, and it's not nearly that, it comes right on up from there. Now let's figure out what the y value is at Did I have that right? Oh, that's the y-intercept over here. Yeah, and we know it's, so it's, get out of there. Okay, we know it's going up. Why is this doing this? Okay, we know it's going up there, and we don't think anything else happens here. It must just keep going there forever. Let's see if that makes sense. Okay? We could plug in another value if we wanted to. We could plug in one more value to the right of this, like maybe 16, right? You know, y-intercept is at 15 and 3/8. Let's do 16. Plug in f of 16. What is the cube root of 16? It's a messy number. It's 2 root 2, I believe it is. I mean, cube root of 2, yep. But you can do it on your calculator. Just do it. 2 times 16 to the 5/3 power minus 5 times 16 to the 4/3 power, and see what you get. I'm guessing it's going to be a positive number. Not hugely positive, but something less than 20 probably. Maybe even less than 10. You do it. 2 times x to 2 times 16 caret parentheses 5 divided by 3 close parentheses minus 5 times 16 caret 4 divided by 3. Open parentheses 4 divided by 3. See what you get. Be sure you put the 5/3 and 4/3 in parentheses after your carets. You want to get it? These calculators are so slow on. Anyone got it? I'm almost certain it's a positive number. Fairly. Second? 2? It could be. It could be 2. It'd just be right here. It'd be up to 2. Yeah. That looks reasonable from my ugly graph, so I think that's what it looks like. Okay? Now, I kind of disagree with their rendition in the book because they have that being a very pointed thing up here, and I'm really pretty certain it's a lot more rounded than what they have in the book. And then you have a pointed flexion here, you have concave down here, and 0 here, and concave up here, and then concave up from there on. So let's check those out now and see. Our first derivatives should be positive from negative infinity to 0. Let's see if that's true. From negative infinity to 0, here's your first derivative, okay? And this thing if you have a negative x in here, take a cube root of it, and you get a negative x. But when you square that, you get a positive x, so you get a pretty big size number here. This will always be negative x in here, and this will be negative, and minus a minus is a plus. So yeah, first derivative is always positive from x equals minus infinity to 0. Okay? And for a little ways after that, your first derivative is also positive for a little ways until you get to your, no, it's negative then after 0. I'm sorry, I was thinking second derivative. Okay. Because after, when you put a positive number in here, for a while, it's a lot of work. Okay, so let's just hang up on that. It's concave down. Oh, let's look at this one. When your x is negative, the cube root of x is also negative, so this will be negative. The cube root of x is negative, but then when you square it, it will be positive. So for a little while close to 0, that's going to be concave. It'll be positive. But then past that, it's going to be negative. It's 0 there, negative there, and at x equals 8, that's your critical value. For sure, that's going to be, your second derivative here is going to be, the cube root of 8 is 2. So this will be 1/2. 1/2 of this will be 10 ninths. And this would be, cube root of 8 would be 2. 2 squared would be 4. And that would be 5 ninths. So it would be 10 ninths minus 5 ninths. So yeah, your first derivative is positive, or second derivative is positive there, and it's positive forever. Okay. So, yeah, concave up from there. So I think we hit it. They put a big, massive table here. Your f of x is negative anytime from negative infinity to 0. Your first derivative is positive from negative infinity to 0. Your second derivative is negative from negative infinity to 0. So it's an increasing concave downward. X equals 0, your function 0, first derivative is 0, and your second derivative is undefined. So it's a relative maximum there. It's not a point of inflection. You don't have to have a point of inflection and second derivative is undefined. You may have, but it's not. Still concave downward between 0 and 1. We found that out. And at x equal 1, your value was negative 3. We had that right. Your first derivative was negative, going downhill, and your second derivative is 0, meaning you have a point of inflection there. Then from 1 to 8, your function is negative. Your first derivative is negative, and your second derivative is positive, meaning concave up. And then x equal 8, you have minus 16, which we made up down there. First derivative is 0, meaning you have a potential critical value, and your second derivative is positive, which tells you that critical value is a local minimum. As that second derivative is positive, that means it's concave up at that point at that critical point, which means it has to be a minimum, relative minimum. Yeah, at 8, the critical number 8 minus 16. Yeah, and 16 is the local minimum value of the function. Okay, not the absolute minimum, because this keeps going downhill forever. Okay, but it is the local minimum. Okay. And then from 8 to positive infinity, your function starts off negative, later becomes positive. Your first derivative is positive from there on out, and your second derivative is positive from there on out. So it's an increasing function, concave, upward. And except for the fact that I think their curve has to be more rounded at 0, 0, I think their graph is pretty good. All right. I don't think we're going to have time to do example 5, okay? So we're going to have to pick up there next time. Oh, shucks, people, we only got 2 examples done this whole period. That's going too slowly, okay? My bad on that. I should have moved it along. Example 5 will include sketching the graph of a polynomial function, which should be much easier. So that should go pretty quickly. Example 6, then we'll have some a trigonometric function, which will have some potential issues with it, but I think we'll do that fairly quickly too. Homework exercises here. I would do all of 5 through 8. Only 5 and 7 will have answers in the back and at calcchat.com, but you should be able to do all 4 of those. Then do any of the odds 9 through 35. They're all at CalcChat. 33 is at CalcView. Do all of the odds. Oh, wait. We haven't done any trig yet, so hang off on 37 on. We'll do those. That's on page 215. Okay. I'll try to move a little faster next time. Yes.
Dr. Pruitt asked me to ask you if you could come to a meeting at 1 o'clock in Dr. Davis' office on this campus.
Yeah, I was planning to.
Oh, you guys, he said check your email. He was like, can you go down there and ask Dr. Powell? I said, sure.
Yeah. At 1 o'clock today, yeah.
On this campus.
Yeah, in Dr. Davis's office.
I'm just
Okay, all right. Thank you so much. Okay. All right. I don't know why they couldn't have waited 2 more minutes and asked me the same question, but that's okay. All right. Any questions before we go? And what you can be doing is what I was about to say. You can go to larsonprecalculus.com and see an interactive version of example 5 before class if you wanted to. And that way you could get a jump on things. Now let me mention a couple more things since I have a minute and a half. I feel like I should be doing something. I just wanted to say I've received 1, 2, 3, 4, 5 out of 15 students. 5 have turned in papers. That's only a third, and we only have a few weeks left. Okay. Test 1, I've gotten all but 1, 2, 3 of those in, so I need test 1 in from the other 3 people. Test 2, I've got 2, 3, 4, 5, 6, 7 out of 15 in, so I need the other 8 of those. So please try to get those to me as soon as you can. And all right, any questions then on chapters, what we've done so far in 3.6? All right, then I'll cheat you out of a minute, about half a minute of your tuition dollars. Thank you so much. And ended a little bit early today. Sorry about that.